Right, I'm going to show you the most common application of the motor effect in the real world, and that is, believe it or not, electric motors. And here's one here. This is actually a demonstration motor for educational purposes, but it does exactly the same thing. Right, what's an electric motor made of? It's made of a coil of wire and a magnetic field. You pass a current through the coil of wire and the coil spins because of the interaction between the magnetic fields of the coil and the magnets, the permanent magnets. Right, I've showed you this last lesson where we have two Magnador magnets. Right, so the pole is on the biggest face. Now, which is which? Okay, we can find out with our trusty friend, the bar magnet. So a north pole is being repelled from that side and it's been attracted to that side. So this face here is the south pole. Okay, I'm just going to write that there. That means that this side here is the north pole. Alright, so which direction is the magnetic field? It's that way, isn't it? From north to south. So the field lines are literally in that direction. Now, there's two sides to the coil, and each will feel a different motor effect force because the current will be going in opposite directions. Now, conventional current, remember, with electricity and magnetism, the rules and the laws always have conventional current. So conventional current is from positive. We've got a rheostat, a variable resistor, otherwise this keeps tripping because there's very little resistance in the circuit. So conventional current goes in here. Now conventional current goes in here and then down this side. So conventional current is going in that direction in the bottom side of the coil. It's going in that direction in the top side of the coil, and the conventional current comes out back to the power supply. Right, let's take the top side first. Which direction was the current? It was that direction, wasn't it? Which direction is the field? That direction. So let's use Fleming's left-hand rule. Right, second finger conventional current. Let's go through them again. First finger field, second finger conventional current, thumb thrust. Right, so top side, conventional current, top side is in that direction, field is in that direction. What do you reckon? So this side's going to be pulled upwards. What about this side? Current's in that direction. That's going to be pushed down. So this side is pushed up, this side is pulled down. Let's just check that. Wait for the voltage. Oh, there he is. Right, so as predicted by Fleming's left-hand rule, okay, this side is pulled up, this side is pulled down. Right, there's a real clever bit here. Okay, now if it was just as simple as that, when this side gets pulled up, when it gets to there, it will just, because it's still been pulled up and because the bottom side is still being pulled down, the motor would stop there like that, which would be pretty pointless for a motor. Now this is the real clever bit here. This is called a split ring commutator. Okay, now what this does, every half turn, the terminals switch here. So the current in the coil changes direction every half turn. So it changes direction. Now, if the current changes direction, but the magnetic field stays the same, the force must flip direction every half turn. So this side here is pulled up, then it's pulled down, then it's pulled up, then it's pulled down, then it's pulled up, then it's pulled down. Conversely, this side here, this side's pulled up, then it's pulled down. This side's pulled up, then it's pulled down. And all because the split ring commutator here is reversing the direction of the current every half turn. Very clever. Without that, motors will not spin. Okay, so let's just get that spinning again. And one final thing, we can turn the voltage up, which increases the current. If we increase the current, that increases the F, and the F equals Bale equation. So it's going to go spin more quickly. Pretty good, yeah? Right, that is how the electric motor works. Simple, really. Thank you.